What we're going to work on next is solving nonlinear systems of equations. We've been working on solving systems of two equations that are both lines, and now we're going to work on systems of equations that may or may not involve any lines. So let's look at our first problem here. We have the equation of a parabola and a line. So this is going to be a parabola and a line. Now, as we know, a parabola is kind of a U shape. So a couple of different possibilities we can have if we have the equation of a parabola and a line. Well, we could have a line that crosses through the parabola. So we could have two solutions. Or we could have a line that entirely misses the parabola. So we have no solutions. Or we could have a line that's what we call tangent to the parabola and just touches at one point. So we could have one solution. So you might have different circumstances depending on how your equations end up coming together. So let's see what happens with this one. First I'm going to go ahead and graph it because it's easy to graph a parabola. We know this is a parabola that is shifted up 4 units and it is not stretched or reflected or shifted left. So we'll just shift up 4 units, put our vertex at 0, 4, and then go over 1, up 1, over 2, up 4. I would go over 3, up 9, but I don't have enough space on my graph, so I'll just go with that for now. So there's my parabola. And then my line has a slope of 1 and a y-intercept at 6. So it's a y-intercept at 6, and then over 1, up 1. And I can see, before I even solve algebraically, that I have 2 solutions, and they will be at these 2 ordered pairs right here. So let's see how that works with the algebra. Since I have an equation that says y equals x squared plus 4, I have another equation that says y equals x plus 6. What we're basically going to do is set y equal to y. So in other words, x squared plus 4 equals x plus 6. And then I'm just going to solve for x. Well, this is a quadratic equation, so I could solve it by factoring, I could solve it by the quadratic formula, or I could solve it by completing the square. So let's go ahead and get started. See what we've got. Let's see. X squared minus x minus 2 equals 0. That looks factorable to me, so I'll go factor it. I have to start with x and x. I have to end, I have no other choice, it has to end in a 1 and a 2. And my signs have to be opposite because the ending sign is opposite. I need my inside and outside terms to equal negative 1x. So it looks like I need a negative 2 and a positive 1. Then the zero product property says that since x plus 1 times x minus 2 equals 0, that must mean that x plus 1 equals 0 or x minus 2 equals 0. Solving for x, I get x equals negative 1 or x equals 2. Now that's fantastic. That's my x value for my ordered pairs. But what I've got to do is go back and substitute those into one of my equations to figure out what y is. So I'm going to substitute into, it looks easiest to work with y equals x plus 6. So that gives me y equals negative 1 plus 6, which is 5. So one ordered pair is going to be negative 1, 5. My other ordered pair, y equals 2 plus 6, gives me 8. So 2, 8. So let's just double check on our graph. Negative 1, 1, 2, 3, 4, 5, that's that one. And 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8. 2, 8 is my other one. So it looks like my graph and my algebra, once again, verify each other. Let's look at another example here. Y equals the square root of the quantity x plus 2 and y equals x minus 4. Okay, this is a square root graph and a line. The square root graphs, of course, look like an eyebrow, as we say. So I guess my line could, if it was very careful, cross through two places. My line could very easily just cross through one place. Or my line could really just entirely miss the radical, so I could have 0 solutions. So let's see which this is going to be. Again, I have a y equals and a y equals, so the easiest way to solve this is going to be to set y equal to y. So I will take my square root of x plus 2 equals x minus 4. Now, in order to solve this, I have to get rid of that radical. Well, the way to undo having a radical is going to be to square that side. So what we're going to do is we will square this side of the equation, and we will square this side of the equation. Squaring a square root basically just gets rid of the radical, so we're going to have x plus 2 equals. On the other side, I have a binomial, so I'm going to have to FOIL that because it's x minus 4 times x minus 4. So that's going to give me x squared minus 4x minus 4x plus 16. So x squared minus 8x plus 16. Now this is one of those quadratic equations again. So let's see what happens when I move my x and my 2 over. Minus x minus 2. That gives me 0 equals x squared minus 9x plus 14. Let's see if we can factor that little guy. 0 equals, has to start in an x and an x. My ending could be a 1 and a 14 or a 2 and a 7. But I'm seeing that I have to have two signs the same, and both signs have to be negative. So negative, negative. And I know that 2 and 7, if I use those, that's going to give me the 9 for the middle. So that's what I'm going to go with. Use the zero product property again. X minus 2 equals 0. So x is 2. X minus 7 equals 0. So x is 7. We're going to substitute those back in to one of these two equations. Let's see, it looks probably like, I'll probably use y equals x minus 4. So that's going to give me that y equals 2 minus 4, which is negative 2, and y equals 7 minus 4, which is 3. So that gives me two ordered pairs, 2, negative 2, and 7, 3. Okay. Now let's see about that graph. With my square root graph, on that radical graph, I know that this is a shift right 2. So on y equals the square root of x plus 2, this is a shift right 2 units. So instead of starting at 0, 0, I'll start at 2, 0. And then there's no stretch or compression, so I'll be going over 1, up 1, and then over 4, up 2, and then I would go over 9, up 3, but that's going to be off the graph, so we'll just go with those and kind of make that general shape of a square root. And my other equation is a line. We have a y-intercept at negative 4 and a slope of 1. So 1, 2, 3, 4, negative 4, over 1, up 1, And we'll connect those dots, and it looks like those two graphs are going to meet up in one spot. Just like that. So let's see what this ordered pair is right here. It is 1, 2, 3, 4, 5, 6. 1, 2, 3. Did I go over 4? 1, 2, 3, 4, 5, 6. Oh, I got 6 too. Oh, I shifted the wrong direction. This was supposed to be left 2 units. Oh, that's what happens when you don't pay attention to your transformations. So we got to cross that one out. So we got to go left 2 units. And then over 1, up 1, over 4, up 2. And now we can go over 9, up 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Oh, look at that. Now they do cross at the right places. Well, it's a good thing that graphs and algebra go together, because it allowed me to catch that mistake. So this ordered pair right here is 7, 3, and that is where my square root and my line cross, which is this ordered pair right here. But what about this ordered pair, this 2, -2? Well, what's going on with that is that a square root graph is actually kind of an inverse graph of a parabola. So if I were to graph the other part of the symmetrical graph, so in other words, when I go up 1, I go over 1, up 1, over 4, up 2, over 9, up 3. If I also went over 1, down 1, over 4, down 2, over 9, down 3, what I would have is kind of the shadow, the bottom half of that parabola, and that's where this intersection would have been. But since this is not a part of the graph, then that ordered pair is what we call extraneous. It kind of goes with the phantom part of that of that square root graph. So when that happens, if our graph shows one intersection, and we actually graphed it right, unlike what I did, if our graph only shows one intersection and our algebra shows 2, then it's a possibility that one of those solutions was extraneous. So it's really important to not only not only solve algebraically, but also solve graphically, or support your answer graphically. And it's also important to graph correctly, but you know, we do what we can. In the next video, I'm going to do a couple more examples and hopefully do them correctly.